Here in section 7.4 we will be solving logarithmic equations. So yesterday we introduced the logarithms. Today we're going to go one step further and solve some equations. A log equation contains one or more logarithms. In these two example problems there's only one log, but we're going to continue the theme of evaluating logarithms sort of and using that log loop, kind of what we introduced yesterday. So let's take a look at this first one. Number 1 here says log base 36 of x equals 3/2. Using my log loop, I can recreate in exponential form 36 raised to the power of 1.5, and we're going to set that equal to x. And we can evaluate 36 to the 3/2 power. If you recall from chapter 6, this bottom digit represents the index. And so if I'm asked to take the square root of 36, raise that value to the third power, then I can solve for x. The square root of 36 is 6 to the third power. We see that our value of x is 216. Therefore, the log base 36 of 216 is equal to 3/2. Let's try the next one. Same idea. We're trying to figure out the log base 8 of x equals 4/3. And so let's begin by rewriting in exponential form. This helps us solve log equations. Okay, so 8 to the power of 4/3 equals x. Now, to rewrite 8 to the 4/3, we can rewrite that as the cube root of 8, because again, my index is 3, so I'm talking about a cube root, and whatever that value is, we will raise that to the 4th power. Let's see, the cube root of 8 is 2, and 2 to the 4th power is 16. So the first part of your homework assignment involves log equations like so. Now we will get into solving log equations when there are two logarithms. And it says if b is a positive number other than 1, then the log base b of x equals the log base b of y if and only if x equals y. So we said right here we have a generic example of hey, if we have the log base 5 of x on the left hand side and we set it equal to the log base 5 of 8 on the right hand side, well then that means that these x's and the 8's, those two components must equal one another. Same is true when you have quantities and not just a single term. In this example, number 1, it says the log base 2 of x squared minus 4, that's going to equal the log base 2 of 3x. And when we notice the logarithms that have the same base, when we notice that, what we can do is what we call drop the logarithms. We can essentially get rid of them, and now we're left with x squared minus 4 equaling 3x. Now it can only happen again is if the bases are the exact same on both sides. Now we have an x squared term, which means, in my opinion, we go right to factoring. We try to see if we can get all the expressions on one side, and then we can set them equal to 0, and then we can go ahead and solve from there. So here we are, x squared minus 4 equals 3x. Let's move 3x to the other side. So the right-hand side reads 0. And now I can try to factor. It looks like it does factor rather nicely. And then my 2x values, 4 and negative 1. Just like the previous chapter, when we solve those radical equations, we have to check for extraneous solutions here. Let me check using x equals 4. I'm going to go back to the original logarithm. The original logarithm is log base 2 of, now 4 squared, which is 16 minus 4, that is equal to 12. And then we have the log base 2 of 3 times 4, which is 12. So that checks out. X equals 4 checks out. Now let's check x equals negative 1. When I look, the log base 2 of negative 1 squared, which is 1, 1 minus 4 is negative 3, I can pretty much stop here, because if we were to evaluate this logarithm by itself, we would see that we would be asked to say, hey, 2 to what power of x gives me negative 3? And no matter how many values of x that you try, nothing with a base of 2, no exponent can be raised with a base of 2 to give you a negative 3. So we say that negative 1, x equals negative 1, is extraneous. So we will go ahead and cross that off and then circle x equals 4. So please be sure to check your work as well. Now I recommend that you pause this video and try example problem number 2. Okay, here in example number 2, if you can follow along some of my work, I found that the 2x values that after you solve this log equation are 5 and negative 3. However, when you plug in negative 3, you get the log base 3 of negative 6, which is just not possible. And so we stop and we say that 5 is our one and only answer.